Hello everyone, welcome back to the fourth episode of the xHCI driver development series. Today we're going to cover a very important topic in xHCI, the command ring. When we eventually start the controller, the command ring is going to help us communicate with it and allow us to actually start talking to connected USB devices, as well as allocate and free resources within the controller. Well, without further ado, let's jump right into it. Before going into the technical details of how the rings are implemented, let's first visualize how the communication between the OS and the controller takes place. The two main pathways for communication are the command ring and the event ring. They're called rings because of their ring buffer structure in memory, but you can think of them as sort of conveyors, onto which one party places their message and notifies the other side, which in turn can pick up that message and read it. It's also important to note that these two rings are unidirectional, meaning that each side should only be concerned with one action, either picking up messages from the ring and reading them, or only placing messages onto the ring. The command ring is used by your OS to place requests or commands onto it. Once your driver notifies the controller that there is a command to be performed, the controller will look at the next available slot in the ring, read the command, perform some action, and finally place a response object onto the event ring, which your OS in turn can read and see if the command succeeded or failed, for example. Similarly, if you place multiple command requests onto the command ring, when you notify the controller, it will go through each request and generate the appropriate responses and place each one onto the event ring. Now you may ask, what are these request and response objects, and what do they look like in memory? The xHCI controller uses what's called transfer request blocks, or TRBs, as units of communication within any of the rings. A TRB is a fairly simple 16-byte data structure that only has three fields: parameter, status, and a control field. The parameter field is usually a pointer to some buffer or a data structure in memory related to the operation. The status field contains information about a command result or transfer length and status. And finally, the control field is used to describe what kind of TRB this is, and contains various control flags that allow tweaking how the controller responds to this request block. Even though individual bits in the control field have different and unique meanings depending on the request type, the following is a generic breakdown of the bit fields that are always there. Bits 10 through 15 are the TRB type field, which is used to determine the command or request type. And the least significant bit is called a cycle bit, and it's used to differentiate new requests from old ones. When dealing with xHCI rings, and the command ring in particular, both the OS and the controller maintain their own copies of the current cycle state, the OS being the producer and the xHCI controller being the consumer. The controller also has its own DQ pointer, which initially will point to the first TRB slot in the ring. As you can see, all of the TRB slots initially are zeroed out and their cycle bit values are 0. Now when the OS enqueues a transfer request block, it will set its cycle bit to be the same as the consumer cycle state. In turn, the xHCI controller will look on the ring and see that the TRB at the current DQ pointer has this cycle bit matching its cycle state and process that TRB. When it's done, it's going to advance its DQ pointer to the next slot. It will then see that the cycle bit of that TRB is different than the current consumer cycle state, so it will stop processing the commands. Similarly, when there are multiple commands placed in the ring, the controller will go through and process each one until it sees a TRB with a cycle bit not matching the current cycle state. At this point, you're probably wondering, what happens when the DQ pointer reaches the last TRB? The controller actually doesn't know how big the ring is and doesn't know how many TRBs it can fit. Well, that is why when setting up the command ring, we set up the last TRB to be fixed and programmed as the link TRB, which will point back to the beginning of the ring. When the controller reaches the link TRB, it will toggle and flip its own cycle state and move the DQ pointer to where the link TRB points to, in this case back to the beginning of the ring. But now all of the TRB slots in the ring have their cycle bits set to 1, so our driver has to keep track of when the end of the ring is reached and toggle its own producer cycle state to match the controller's new consumer cycle state and stay in sync. This way, when the new command is ready to be enqueued into the ring, its cycle bit is going to match the new consumer cycle state and be different from the rest of the TRBs in the ring. One little side note, don't get scared by the terminology of producer and consumer cycle states. In practice, it's really simple, and your driver just has to maintain the command ring's current cycle state, and when enqueuing a new request, just set the TRB cycle bit to be the same as that. That's it. Now let's jump into the code and see it in practice. Alright, so the first thing we're going to do is create a new file, xHCI trb.h. This is where we're going to keep all the definitions of various types of TRB structs, like different command, transfer, or event completion TRBs. For now though, let's just create a generic TRB structure. As we saw in the diagram, a transfer request block has three main fields. The first one is an 8-byte parameter field that encodes request-specific parameter data. Following that, we have a 4-byte status field, simply encoding the current TRB status. And finally, we have a 4-byte control field encoding the control bits of the request block, such as the TRB type. Now, to make things easier for us going forward, so that we don't always have to suffer through using bitwise operations, we can define a union here and describe bit by bit what the most common TRB control bits are. Now, the first bit is one of the most important ones, and it's the cycle bit. It helps the controller differentiate between new and old TRBs in the ring and helps track when to loop around the ring buffer. After that follows a series of 9 bits that are most commonly used in transfer TRBs on transfer rings, but we haven't covered that yet, so we won't introduce them yet. For now, we'll just mark them as reserved. Then we have the TRB type field, which is 6 bits long and is used to identify the TRB. And finally, after that, the rest of the bits are reserved and zeroed out. One very useful thing to do now is put a static assert statement checking the size of our struct and making sure it's exactly 16 bytes long at compile time. This neat little statement here saved me numerous times from atrocious bugs when dealing with giant structs with tons of bit fields of varying sizes and accidentally messing up the length of one of the bit fields, causing the whole struct to get misaligned. Now that we have our TRB struct, let's go ahead and implement the command ring. For that, let's create a new file called xHCI rings.h, and this is where we'll keep all of our ring classes. Let's include xHCI mem to access our memory allocation functions, and xHCI trb.h to access our newly created TRB struct. Now for the command ring, let's create a separate class. And let's make the constructor take in the maximum number of TRBs this ring can hold. This means that the ring cannot grow dynamically, so we'll need to know the number of TRBs we're going to store there ahead of time. And we're also going to create a public function to allow to enqueue or insert TRBs into the command ring. Now we gotta define a few private member variables. First, let's define a size t max TRB count to hold the number of transfer request blocks a ring can contain. Then we'll create another size t variable called the enqueue pointer, and this will keep track of the position or the index where we can insert the new command TRB. Then we also need to keep track of the actual TRB buffer, and we'll store that in m_TRBs. We will use this to actually place TRB blocks onto the ring. Now to make our life easier, we'll also create a variable to store and keep track of the physical address of the ring to provide to the controller. And finally, we'll have a variable to keep track of the current ring cycle state bit. The last thing I want to do here is create a few getters for the virtual and physical bases of the ring as well as the ring cycle, just to be able to access them outside of the class. And we're done with the header file. Let's go and implement the xHCI rings.cpp file now. The first thing we gotta do is implement the constructor, where we actually allocate the ring memory. First of all, let's save the max TRBs value into our member variable. Then we have to initialize the ring cycle state to 1 and the enqueue pointer to 0, aka the first slot. Now let's calculate the size of the ring buffer in bytes, so that will be max TRBs multiplied by the size of the TRB structure. Great, now we can actually allocate the memory for it using our good old alloc xHCI memory function call. For the size, let's pass the ring size we just calculated, and for the alignment and boundary arguments, we'll use the macros we defined in the first episode in xHCI common.h. To be exact, the command ring has a 64-byte alignment requirement, and it must not cross a 64 kilobyte boundary according to the official xHCI specification. Great, now that we've successfully allocated memory for the ring buffer, let's also get its physical base address and store it in our member variable. Now this is going to be a very important part, so don't forget to do this. We need to set the last TRB in the command ring to be a link TRB, allowing the controller to recognize the end of the buffer and circle back to the beginning when fetching commands. First, we need to set the parameter to be equal to the physical address of the beginning of the ring, so the same as our physical base address that we already saved. Then we have to set the control bits, and for the link TRB, I will actually prefer using the bitwise OR operators rather than the bit fields that we defined in the TRB struct. First, we must set the type to the link TRB type, which is a value of 6, and then shift it left by 10 bits, which is equivalent to just setting the TRB type bit field in our struct. Then we have to set the second bit, which for the link TRB is a toggle cycle bit, and will tell the controller to toggle its internal ring cycle state bit. You know how we're keeping track of the ring cycle state in our class? Well, the controller is doing the same on its own side, and this bit will tell it to update and toggle it. And finally, we have to set the cycle bit to the value of our current ring cycle state, which is right now 1. Now that the constructor is done, we can implement the enqueued function, which will take as an argument a pointer to a transfer request block that we want to put into the command ring. First thing we have to do here is set the TRB's cycle bit to be the same value as the current ring cycle state in order for the controller to recognize it as a new TRB on the ring. Then we can insert the TRB into the ring buffer by doing a simple memory copy. Now that we've successfully put the TRB onto the ring, we have to advance the enqueued pointer and check for a wraparound scenario, in which case we have to first update the link TRB to contain the updated ring cycle bit, then set the enqueued pointer back to the first slot, so back to 0, and finally toggle our own variable that tracks the ring cycle state. And that is it for the command ring class. Let's now go back into our xHCI driver class and integrate the command ring into it. In the class header file, I'm just going to create a member variable for the command ring. And here I'm going to use my kernel's version of the C++ standard shared pointer object to do that. Now going into the xHCI.cpp file, let's revisit our configure operational registers function, where we set up and configured DCPAA as well as a couple other operational registers in the last video. And now that we have a command ring, let's replace the to-do comment with code to actually create the command ring instance. As for the max TRB count, a good initial value for our driver to use is going to be 256. And conveniently enough, we have a macro in the common header to represent that constant. After successfully creating our command ring instance, all we have left to do is write the appropriate value into the command ring control register, or CRCR, in the operational register set. And that's going to be the physical base address of the command ring, ORed with bit 0 being set to the initial value of the command ring cycle state that the controller should use. And that is it. Even though we won't be able to test out the command ring usage until after we have started the controller again, because as you remember it is currently halted and reset, let's still compile and run the project to see if the CRCR register was set correctly. And as you can see, the CRCR was indeed written to correctly with the physical address of the command ring, and the rightmost bit is set to 1, indicating the correct ring cycle state. And that is it for today. Congratulations on getting one step closer to starting the controller back up and detecting connected devices. In the next part, we're going to explore the runtime register set, slowly introducing things like the port management registers, the doorbell register array, and the last step before starting the controller back up would be setting up the event ring, which is going to be really exciting. Thank you guys again for watching, and I hope to see you next time.